So good afternoon. Today our speaker is Khanna, who got his PhD from the University of Sydney, studying the Gala spectroscopic survey. Then he moved for a postdoc at Kaptein Institute in Groningen. Since 2019 and until now, he joined his part of the Gaia collaborations. In particular, he was within the validation team for the E and DR3 releases. And he joined INAF in Turin, and there he's member of the Gaia Unlimited collaboration. He's an expert on connecting dynamical structures in the galaxy to the velocity distribution of stars. And he can start his talk whenever. You should share the screen, of course.
Are you able to see my screen?
Yeah, go full.
Okay, let's see if this works.
Okay, you are in control, please.
Okay, great. Right, well, first of all, sorry. Good afternoon, everyone. And I send my apologies. I couldn't be there in person, just the schedule of this week. But anyway, thanks for having me. So yes, I'm Shaurya, and I joined the INAF here in Torino in April last year, where I work primarily with Ron Drimmel, but also with colleagues both in and outside of the Gaia collaboration. And so this talk is about one of the projects that we worked on recently, with using mostly Gaia data. And in fact, the image that you see on the title slide is also from the survey itself. As many of you would recognize, it's essentially a density map of sources that have been observed with Gaia, and you see quite clearly lots of familiar features of the disk. You see the central bulge region. You see the satellite dwarf galaxies, LMC, SMC. You see the disk. You see the dust lanes. So in this talk, I'll try and show some recent work where we can try and connect the central parts of the disk to the outer disk. So I'm sure many of you are familiar with the Gaia survey, so I have a very simple overview here. But essentially, if you are interested in the kinematics of stars, then you want to know where they are on the sky and how fast they're moving. And essentially, that's what the Gaia survey was designed to do. So it was launched in December 2013 and has been observing since about 2014-ish. And basically, for most people, what it gives you is a set of what we call 60 phase space coordinates. So it gives you the sky position, and then it gives you a measure of how far the stars are in terms of their parallaxes. And then, of course, you also get the transverse motion. So you get the proper motion information of the stars, how they're moving across the sky. And for a brighter subset, you also have information about how fast these stars are moving across the line of sight. So when you combine all of that, you can kind of make this 3D velocity map together along with their positions, and then look at how they're moving with respect to a model, say. So here's just a brief timeline of what the survey has been doing. It had its first data release back in 2016, but the major release really happened in 2018 when we had the astrometry for about 1.5 billion sources. And as I mentioned, line of sight velocities. It says radial velocities, but I tend to prefer using line of sight or V line of sight because to me that's a bit more intuitive. And radial velocity can also be this component, which is galactocentric. But anyway, the point being that over the years, as the baseline for the satellite has increased, the precision in these quantities has also improved, and also the sheer numbers have increased. And also the output has become more sophisticated from not just the photometry and astrometry, but also several value-added catalogs that people across the astronomy community now use. And to appreciate that, you can kind of compare it with the previous major astrometric mission, which was the Hipparcos mission. So here's just an illustration of the volume that was covered by Hipparcos. This is on the scales of a few hundred parsecs. And then if you go to what Gaia has given us, so starting from its first data release all the way up to now, depending on what population you are studying, we can really probe a substantial chunk of the disk now. And really, we can go all the way from the inside to the outside of the disk, including looking at fainter objects in the halo, for instance. So it really is allowing us to answer questions that we've been seeking for quite a while. So as I mentioned, there are a bunch of catalogs that came out. So this is this illustration is for the latest data release, which happened in June last year. So of course you have the standard astrometry that comes with all the releases. This hasn't changed since the early release, which was about a year before that. But you now also have many new objects that are of interest to the wider community. So we've got a catalog of the quasars, for instance, and of binary stars, and this has been generating lots of interest. But for this talk, mainly what's of interest is the new set of line of sight velocities. So we have about 33 million sources now for which you have these line of sight velocities, and so you can essentially build the 6D phase space for these sources. In addition to that, there is also a huge number of astrophysical parameters. So this is, effective temperature, metallicities, log G, that allow you to select subpopulations and so look at the kinematics, not just spatially, but also in terms of the chemistry of the galaxy. So of course, as I said, it's not just about the sheer number of sources that we can now start to look at with Gaia, but also the precision. Of course, we had proper motion information for stars even before Gaia, but you can appreciate the improvement that one now has access to thanks to Gaia by looking at this uncertainty plot of the proper motions from the UCAC catalog, which was extensively used pre-Gaia. And you can see here, this is just an uncertainty as a function of magnitude. Compared to EDR3, where at magnitudes less than 15 in G, the improvement is almost a couple of orders of magnitude. And even at the fainter magnitudes, it's still much better than what we had before. And this is also for stars that are much further away. And so, if like me, it's easier for you to look at the uncertainties and velocities, then here's an example of the sources along the anticenter line of sight, where you don't have to use the V line of sight, for instance, to look at the velocities. And you can see out to a very large distance. It's a galactocentric radius, so out to about 15 kpc or so. The errors in the azimuthal and the vertical velocities are well below 7 kilometers per second for a majority of sources. So this is kind of highlighting what kind of proper motion improvements we've been enjoying thanks to Gaia. Of course, the Milky Way has been surveyed for several years, and in particular, the last decade has been really. But we've been really fortunate to have several surveys looking at the galaxy altogether. However, these are spread across the globe, and so one of the consequences of that is that you get sparse coverage on the sky. You can, of course, go much fainter depending on your instrument's capabilities. But even if you put all of those numbers together, for the highest resolution spectroscopic surveys, we still have only about a few million stars at most, for which you have crucially the chemistry from these surveys, but also the line of sight velocities, which of course go down to precisions of almost 0.1 kilometers per second in the high resolution case. But typically we have about 6 to 7 million sources for which you have these information, these line of sight velocity components. So this has of course been really useful because people have been able to explore what the disk has been doing. But now we can combine this with the new Gaia line of sight catalog and really push the boundaries in terms of the precision and in terms of the extent. So here's just showing you what a compilation of all the spectroscopic surveys and Gaia together looks like, and clearly you can see that now we are in this era where the line of sight velocities from Gaia tend to dominate. And then of course you have the low resolution surveys like LAMOST, which provide the majority of line of sight velocities. And as I've been talking about the precision of the line of sight velocities, just final slide on this. compared to the previous Gaia release, we've now managed to go down further 2 magnitudes in the completeness of these sources, which means that we can now probe the 60 phase to an even larger volume. And if you look at the precision for the brighter stars, certainly it is getting quite competitive in terms of the ground-based spectroscopy, and even for the fainter sources, the errors are still quite decent that allow us to do various things. So of course, thanks to all of these surveys, we have been observing various parts of the disk, various parts of the galaxy across wavelengths, and that has been really useful for us to try and put a picture together. So on the left-hand side here is a model of the interior parts of the galaxy based on surveys done with red clump stars, the infrared, so that you can peer through the dust in that region. And what that has shown us quite clearly is the presence of a strong galactic bar. And not only is there a bar there, but this density map also shows you that it's orientated at an angle with respect to our line of sight here at L equals to 0, about 20 to 25 degrees or so. And then if you look at the gas distribution of sources, in this case, you can do this, for instance, with massive stars, so with masers. That allows you to build, these kind of models of the spiral arms of the galaxy, which of course spread across several kiloparsecs. So this is a model from Reed et al., where they have about 4 main spiral arms in this case, all traced by these masers. And now, of course, with Gaia, we can do the same kind of thing, but much more locally. So this is work by Eloisa Poggio, for instance, where she looks at the local spiral arms by carefully selecting hot young stars. And we can see that not only do we have, of course, these spiral arms that we've known for a while, but also they have fine structure within them. And then since we have excellent distances and velocities for these sources, we can then try and correlate what the spatial and the velocity maps tell us together. Of course, in the outer disk, the disk also flares, and we know there's the warp. So we know that if you put all of these ingredients together, we pretty much have a galaxy that is not axis-symmetric. We have a lot of these non-axisymmetric features at different scale lengths and scale heights. So if you're interested in the kinematics of stars, you want to know what the influence of each of these is on the velocity field. Okay, yeah, and of course, this is something also that's a long-standing investigation. So we've done this all the way back from just simply photometric surveys, but also as we started having much larger spectroscopic surveys and started getting the line of sight velocities, we could then start to build the kinematic maps and see what was going on. So here's an example from the RAVE survey where they found that if you for the sources for which you could get the 60 phase space, this is galactocentric Z and R, so the sun sits at about 8 in this case. What you find is that in the galactocentric radial and the vertical components, you find all sorts of gradients, both in terms of the radial distribution, but also vertically. So both in and out of the plane, you find velocity gradients. Now, for a perfectly axisymmetric disk, one would expect these components to be about 0 at the level of the noise. But that's clearly not the case, and you can see the amplitudes here are almost 10 kilometers per second in the radial velocity, for instance. Also, we find not just the gradients, but we also find wave-like structures. So you find stars going up in one part of the, let's say, the interior, and going down in the outer disk. So we have this bending. We have bending modes in some cases. We have breathing modes in other cases. So there's a lot of there's a lot of, if you like, perturbation effects that were already noticed in the past decade or so. And the amplitudes of these are important because the amplitudes of these if we can model them, then we can relate them to the individual features. So in this case, this is work that we did with trying to measure the streaming motion in the line of sight velocity components, and we found that it was of the level of about 7 to 8 kilometers per second, and there have been models that have suggested that maybe the bar or the spiral arms might be causing these. So continuing that with Gaia, just shortly before we had DR3, we did a similar study where now, of course, since we're not limited with the number of sources for which we have the 60 phase space, we could construct the models directly from the data. So in this case, you assumed the galaxy is axisymmetric, and then you use the rotation curve that you get directly from the data, and then you can subtract that. So if you parameterize that in terms of some coefficients and in terms of the scale length and scale height, then you can subtract that off and derive all the other velocity components. In this case, the radial, the VZ, as well as the line of sight velocity components, and then look at the residuals. And again, if it were a perfectly axisymmetric system, you would expect this to be about 0, and these and the power spectrum that results from this kind of map to also be, the power spectrum of the noise. But it's not the case. As I mentioned earlier, we see quite clearly that there is streaming in the radial component across the disk, followed by streaming in the azimuthal component and the vertical, and so on. So when you compare this to models, you can get clues about the properties of the spiral arms themselves. You can relate these to the co-rotation radius of the individual spiral arms. So thanks to Gaia, we're now able to do this. So this was for 9 million sources for which we had radial velocities. There was no population selection here. But last year, as part of the Gaia data release, we had a paper where, to demonstrate the capability of Gaia, we showed what one could do by carefully selecting a population of sources. In this case, from the 33 million sources, we could select RGB stars, and we could select OB stars, which are younger stars, as well as Cepheids. So we have an older population, we have a younger population, and we have a population that can trace, for which we have excellent distances. And the benefit of that is then, for instance, if you make the rotation curve, you can trace the rotation curve over different radii, and also we can look at how each different population is behaving, for instance. So for instance, for the Cepheids, distance errors in this case are less than 6% at a distance of almost 10 kpc. So we really can trust what's going on in the outer disk with these, thankfully. So with the giants, the benefit is that you can probe both the inner as well as the outer disk at the same time. And that's very well illustrated by this map over here, where you have the galactocentric radial velocity mapped. So in this case, a negative VR means that stars are moving inwards towards the galaxy, and positive means they're moving outwards. And quite clearly, I mean, I don't have to point it out, but you can quite clearly see that this quadrupole pattern is picked out. And that is, of course, a very strong kinematic signature of the galactic bar that I showed earlier in the surface density. And what's also interesting about this map is that you can see pretty much the same detail both in the interior as well as the outermost part of the disk. So this is the kind of map that now allows us to go beyond just looking at maps, but maybe also comparing these two models. Of course, this quadrupole pattern is not really new, because even with apogee data, where they had really precise distances for a select number of sources, they could already see hints of this. And what's encouraging to see is that we find pretty much the same orientation and pattern speed as them. So essentially, we find that the bar seems to be a long structure with a co-rotation radius of about 5 kpc, and it has a pattern speed of about 38.1 kilometers per second per kpc. And you can see on this map that also in the outer disk, there are all sorts of little features that might be related to the bar itself. So it's hard to ignore whether or not there's a large scale influence of the bar on the outer disk kinematics. So going back to this rotation curve, here, of course, we have the different populations together, but if you look at just the Cepheids, which are these black points, you might have already noticed that around about 13 kpc, there seems to be a gap in this rotation curve. And this gap isn't a vertical stripe, but rather a diagonal line, which, if you think about it, in the R cross V phi space, this diagonal line corresponds to the angular momentum of the Z component. So this gap seems to be a gap that is in the angular momentum, which is, you can see that clearly now. It appears as a horizontal line if I plot the same thing in terms of LZ. And if you make a histogram of that, then it becomes quite clear that indeed in the Z component of the angular momentum, you have this gap. This gap, if you look at the width of the gap, it's much larger than the uncertainty for this value, which is in normalized units, it's about 1.42 times the LZ of the sun. And since it's a gap in conserved quantity like angular momentum, we think that this might be a hint of a resonant feature. So to explore this further, we actually then went ahead and looked at in a different space. So I want to spend too long on this, but basically you can also look at conserved quantities in terms of action angle coordinates. You've already seen one of these, which is the J phi, but essentially these coordinates just come from the fact that as stars orbit around the galaxy, they do so in epicyclic orbits around a guiding center. So actions are a way of quantifying how they vary in their orbit. So you can the J5, for instance, gives you a measure of where the guiding radius is. The JR gives you a measure of the eccentricity, and the JZ is the same thing but vertically. So it gives you a vertical excursion. And so in this space, if the galactic potential is either slowly varying or if it's perfectly axisymmetric, then these coordinates are supposed to remain invariant or conserved. And so if you assume a potential, sorry.
20 minutes, sorry.
Okay, sure, yeah. And so if you assume a potential and estimate the actions, there are simulations which show that for a galactic bar, let's say, if you have a galaxy with just a galactic bar, in this space and actions, you are supposed to see certain bridge-like lines which correspond to where there should be resonances. And these resonances essentially arise from the fact that if you have ratios of the pattern speed of your perturber, in this case the galactic bar, and your angular frequencies of the stars, then if you have an integer number combinations of these L and M numbers, that gives rise to these resonances. So for the bars that we find in Gaia DR3, for instance, the two main resonances that I wanted to highlight are the OLR, the outer Lindblad resonance, which occurs if you have 1 equals 1 and 2, 1:2 line, and the other one is the 1:1, which is this 1.42 line. What's interesting is that this value pretty much lines up with where we see the gap in the Cepheids. Now, if we look at the action space for our data, and if I plot the lines of the resonances, then in this plot, you can see that this is again LZ. So you can see indeed there are lots of these ridge-like features over here, but in this density space map, it's very hard to pick out anything in the outer disk. And this could be because of two reasons. One, that most of the sources for which we have radial velocities, line of sight velocities, are indeed much closer to the sun than are further away. So it's a bit more diffuse out here. But also in the outer disk, the vertical excursion of stars is much higher. So again, that also adds to the diffuseness of this, if you like. But there's another way in which you can increase the contrast, and that is that along these resonance lines, one is expected to see stars either being trapped in orbits or being scattered around. And that gives rise to an uneven ratio in the number of sources moving inwards versus outwards. So if we now map the same thing by this quantity, then you see that now all of a sudden you are indeed able to pick out a lot many more features, first of all. But secondly, both along the OLR, where you see it lines up quite nicely between this blue-red feature, but also along the 1:1, you now see that there is this distinct gap that occurs in this substructure. And what's interesting is that in a previous DR2 work that was led by Frick et al., they were missing this data coverage because, of course, they were limited by the data at that point. So we're now able to fill in that gap. So the whole point of this is that we see the gap in the Cepheids, which is a young population, and we are also able to trace something similar going on in the older, much evolved RGB population. So if it's a dynamical process that's causing this, then it shouldn't really discriminate in terms of stellar ages, and that makes us think that maybe this is indeed a resonant feature that we've now managed to detect with this. How long do I have? Do I have a couple of minutes or so?
Yeah, sure. Go ahead.
Okay, great. So, so assuming we are convinced that we are indeed seeing this one-to-one resonance, maybe for the first time so clearly, we can actually use this to our advantage. So if you just plot the angular velocity of stars as a function of radius, let's say for the giants, in the paper, since we derived a pattern speed for that, we could predict where these resonance lines would be. But now if we instead use the value of the gap and say that is the resonance line of one-to-one, and we use the data directly from Cepheids. Now, since the Cepheids have a lower velocity dispersion, one would trust the angular velocities to be much more closer to the circular velocity. And so you can invert this process and essentially derive another pattern speed of the bar independently, if you like. And we find that this is quite close to the value that we derive from the RGBs. In fact, it's within the uncertainties that we find. So round about between 38 and 43 kilometers per second per kpc is where we think the pattern speed of the bar is. Just very finally, are there any other possible origins of the gap? So far I was just concentrating on the resonances, but of course our galaxy is not isolated. And so you can also think of what might be happening if, say, a strong interaction between the Sagittarius dwarf galaxy and the Milky Way takes place. Of course, we know such a stream exists, so it's interesting to see what sort of interactions that causes in the velocity maps. And so this is an example of that provided by Thorsten Tepper-Garcia, where he just takes an impact of Sagittarius, and he shows that over time you can generate all sorts of bending waves in the disk that can cause all sorts of gaps in the distribution. In fact, if you look at the vertical velocity distribution of sources from Gaia DR3, you indeed find there's a break in the velocity that was discovered shortly after EDR3, and this was completely new. We'd never seen this before. So the question is, could this gap be related to the gap that we're seeing or not? Because a simulation where the Sagittarius dwarf is interacting with the Milky Way can cause something like that. So here's the short answer to that. Indeed, that gap that we see from the Sagittarius passing is very close to the value of the one-to-one resonance, but it is still quite distinct. So this is the same break that I showed in the previous map, and you can see that it sort of lies in between the OLR and the one-to-one line. So of course the outer disk is quite messy. So it must be. There are likely multiple origins to all sorts of features that we see. You could have internal resonances, which in this case seem to match with what we see with the bar, but you also have signatures of what the disk might be doing with interactions with its satellite galaxies. But for now, it seems like this feature might indeed be a distinct feature. Okay, I don't know if I have too much time, but there was a recent follow-up paper to our work where people went, where Martin Semzuk and group, they went out searching for these kind of gaps in cosmological simulations, in this case, looking at the Illustris suite, where now you're looking at not just the bar, but also a galaxy which develops bar and spiral arms, and to see whether young stars, like the ones that we see in Cepheids, whether when they're star forming, whether the gaps that we see could just be because of gaps between spiral arms or not. So of course, they show that you can produce these kind of gaps in that, but in their paper, it's also quite clear that these kind of gaps are limited in the azimuthal bins. In other words, if you were to look for the same gap across the azimuth, you wouldn't find that. Whereas if it's a resonant feature, like in the case of our Cepheids, which we think it is, if the same gap should show up everywhere. And essentially, we went ahead and just did a quick check with our Milky Way Cepheids to see if you could trace the same spiral arm across the azimuth or not. And I think this is the plot that I want to show quickly, which is that if you look at where the angular momentum gap is as a function of the azimuth, selected for one of the spiral arms, which is in the outer disk, you indeed see that it crosses across the azimuth. So the gap is not is not necessary. It's not simply because of gap in the spiral arms. Although of course that can also complicate things, and I'm sure that also happens, but maybe on a different time scale. Okay, so I've probably run out of time, so I will just summarize quickly. So essentially, thanks to the quality of data from Gaia, we've managed to use the population of giants as well as a population of Cepheids to find signature of some of a resonance-like feature in the outer disk. And the location at which this occurs seems to kind of match if the predicted resonance lines for a galactic bar like ours. This interaction, is it necessarily because of the galactic bar, or could it also be a result of some resonance with the spiral arms? That is another possibility, and maybe more simulations might shed some light on that. But either way, the outer disk is quite an interesting place, and now we're able to find many more detailed substructure in that. So I think I'll stop there.
Okay, thanks. Questions for our speaker from the Carlo? Let's pick up. Let me check if there is anything online.
Yes, I have a question actually on the first part of your talk, when you were showing the mean vertical velocities of stars, the map. And you, if I understand, you were saying that this is not expected if your system is perfectly axisymmetric. And I wonder whether this is true in general, or you might have some meridional motion or something like that. And also, if you, what kind of asymmetry you are kind to infer? Is asymmetry with respect to the equatorial plane, or triaxiality, or something like that?
Right. Okay. Yeah. Sure. So yes, when I say axisymmetric, essentially that is the symmetry in terms of the azimuth. So of course, if you had a galaxy that had no spiral arms, then as you scanned the velocity field across the azimuth, you would expect it to look pretty much the same. There shouldn't be a directional, dependence on what you see. So in terms of the VR, for instance, that I mean, this follows directly from that, because if you have at the location, at the boundaries of where you have the spiral arms, you can get stars depending on whether you're inside or you're outside the arm. You can get pulled or pulled away, and so that can cause all sorts of, if you like, residual velocities at those boundaries. So that is why if you didn't have that, you would think that it's it should be at some level of around zero. It should be just a Gaussian, if you like, distribution. For the VZ, I guess it's the again, if the galaxy wasn't warped, if the disk wasn't warped or flared, then again, I guess you could simply divide it into two hemispheres, and then you would also expect, if there is any vertical oscillation, it should, over time, it should just be a Gaussian. But of course, that's not the case, because in fact, the spiral arms as well, they not only scatter the stars in plane, but you can also see that they have an effect. Models show that they also have an effect above and below the plane. So that is what I meant by that. And I think you had another question, or did I miss it?
No, I think you answered that. I mean, so when you say non-axisymmetric, you mean mainly spiral arms, not like an effect of bar or something like that.
No, that too. It's just that the scale length of the spiral arm is a lot more. I mean, it's a lot higher. The bar. I mean, it's a good question, because the bar, of course, depending on what mass it has, one would expect its sphere of influence, if you like, to be out to some radius. In fact, I think the potential of the bar goes as r to the minus a third, or 1/3 or something. So that means that so it's a good question to ask whether the outer disk, let's say at the values at, let's say 13 kpc or so, do you really expect a strong resonant effect of the bar or not? Certainly inside at the OLR one, we do, because we also see other features, with the UV velocity, for instance, we've seen the Hercules stream, for instance, and so that has been related to the bar already. But yeah, I think because of the scale length of the spiral arms, one would expect that that those would probably dominate more in the outer disk. Yeah, but of course, yes, no. I think you certainly have to take into account all of them. In fact, even with even in the halo, I think people have seen the effects of the resonance with the bar. I think it's a PAL5 stream, and that has also been shown that the gaps in the stream have been caused by, could be caused by the bar. So we can't neglect any of that now. Yeah.
Other questions from the room? Yeah. You can just pick up. You don't.
Yeah.
Really
Oh, okay. Very good.
It's working very well. Try.
In the next slide, you have shown that the giants appear to rotate slower. Maybe one more slide. There is a plot, the rotational plot of, here. So the giants have a slower rotation curve? Does it say something about evolution?
Right. Yes. So of course this is the rotational curve. This isn't the circular velocity, and I think I alluded to that later on. If you were looking at the true circular velocity for each population, you would have to take into account the asymmetric drift. Yeah, I mean, so because the drift affects more the giants, they're the older population that get scattered more. Yes, so I think that's why you see this. I mean, this is a median line, so it also gets affected by number counts and things like that. But yeah, I think that's the reason why you see a difference here. Yeah, which is actually why when I showed the angular velocity curve, if in principle you could sample the same number of I mean, the Cepheids here are only 2,000 compared to about 6 million. But if you could have, let's say, a boost of the number of Cepheids here, that would be, I guess, the true circular velocity curve of the Milky Way. Yeah.
Thank you.
I see no other questions. So thanks again. That's it for today. Thanks a lot.
Thank you.
And let me stop the recording. There were no questions from the audience right now.